Okay, class. Now we're going to talk about applications involving variation. So these are the word problems that most of you aren't real fond of, but they're a part of life. Genuinely, most math that we use in the real world comes from word problems. So we're going to start with this little setup that I've kind of done to walk through the procedures. So first, write a general variation model that relates the variables given in the problem, and K is going to represent the constant of variation. You don't know what K is at this point. You're just writing the equations, kind of like what we were doing before in both the direct and inverse variation and in the joint variation. We're just writing the problem out. Step 2, we're going to take what they've given us and we're going to solve for K. We're going to substitute our known values of the variable into the model from the previous step, and we're going to solve for K. So they give us some information. They tell us at this point this happens, or at this time this happens, at this height this happens, whatever it may be. And then after that, we're going to use that information to solve for K. Once we know K, then we're going to go back to the equation. So now we're going to go back to the equation. We substitute the value that we know is K in and replace K into our original model. And then we're going to take the information we want to know about. So maybe we know at a particular height of something, we might be able to tell that the pressure on the airplane is at this much. And then as it goes higher, the pressure decreases or is inversely proportional, whatever it might be. And we may be able to say, okay, we know here it's this. What is it when it gets to this height? And so we use this idea, this variation model. We figure out what that is at this height, and we get the constant, our K, that number, whatever it may be. And it could be a decimal. It could be pretty ugly, actually. It could be a fraction. It could be just a whole number. And then we're going to now apply that information to our base equation. And now we're going to go up. We're going to say, well, what is it when it's this high? And we can do that using variation. So that's what we're going to do. We're going to walk through a couple. So here, this is just in general. We're told that A varies directly as B and inversely as C. So that's the statement here, and varies directly. Remember, that means there's a K times, in our case, the B. And then inversely is the division, and we have C. So our general variation model is A is equal to KB over C. Pretty straightforward. If A is 20, so we're going to substitute the values into the model to solve for K. So the values say that A is 20 when B is 4 and C is 5. So I have this exact equation, and I'm going to go and say A is 20, and that is equal to, I still don't know what K is. K is what I don't know. But I know that B is 4, so I have 4 times K over C is 5. And then to solve this, I would, let's see, can I get that one to pop up for me? There it is. Ink. Come on, do it again. Ink tools to give me a different color here. Okay, so I'm going to multiply both sides by 5. That'll filter that off. And then I end up with 5 times 20 is 100 is equal to 4K. So then I'm going to divide by 4. And do that in a, I guess it really doesn't matter, but let's just do that. So we're going to divide it by 4, divide it by 4. So this means that K is equal to 25. So now that I know what k is equal to, I can plug it back in. So again, the original equation is A equals K over B, or KB times C. And so this becomes A is equal to, K is 25, so it's 25B over C. Then it asks me to find B, B is what I'm looking for, when A is 30 and C is 20. I know A, it's 30, so I have 30 here. I also know I have 25B, B is what I don't know, and it's divided by C, which is 20. Well, the first thing I want to do is simplify that. I want to say, okay, or maybe not, I don't know. To me, I would simplify it. I would say that 5 goes into both those, so it's 5 over 4. But you guys may not see that, and that's okay. We don't have to see that. Let's just go ahead and maybe do it like it is first. Or maybe I will simplify this. So this becomes 5 goes into 25 5 times, 5 goes into 40, into 24 times. So then all I have to do is multiply by 4 and 4. So then that filters off. This is then going to be, what's this going to be? This is going to be 4 times, so 120, 4 times 30 is equal to 5B. Divide by 5, divide by 5. 5 will go into there, that's 1. 5 will go into 12 2 times. That leaves me 20 left over. 5 will go into 24 times. So B is equal to 24. And this is the process. So first, write it as a general. Write it generally by what it says. Then substitute some known. Usually that's in your first part. And in this case, it's telling you specifically, right? If this is known, then you have this and this. So you plug those all in and you solve for your K. That's where we're solving for our K. We got to figure out what K is. We then plug it back in, just the K, back into our original to get our new workable equation. Then find out with the other piece what they want. So then find this piece when this is true. So our initial equation, solving for K, then plugging it back in, then substituting them in the new value to solve for the variable they want. So this is the process. Let's try another. So the speed of a racing canoe in still water varies directly as the square root of the length of the canoe. So we need to figure out how we would write that. Speed, so maybe we use S. So let's say S is the speed. Or we could just use miles per hour. Let's use miles per hour. That's a speed. So we have mph, that's my speed. This is this. And in still water varies directly, so this is the K times as the square root of the length. Square root of the length. So a square root, and I'm going to put L in there. I'm going to do L because that's what we're talking about. So then this is just equal to K square root of L. So then that's great. We have a equation. Then we say, okay, what do we want to do with it? We want, if a 16-foot canoe can travel 6.2 miles per hour in still water, 6.2 being my speed, 16 foot is my length, find K. So we have 6.2 is equal to some K times the square root, and I have 16. Well, the square root of 16 is 4, so I have 4K is equal to 6.2. So then I'm going to divide by 4, divide by 4. So K is going to equal, 4 will go into 6.2, 1.55. So that's what K equals. And if I want to find the speed, so then I should write a new equation, right? But if I want to, my new equation, what would that look like? Well, that would look like knowing this K, but I'm still using the same equation up here. I would have MPH is equal to 1.55 square root of L. That's now a workable equation I can use to solve these. So if I want to find the speed of a 25-foot canoe, I'm going to do exactly what you think. I'm going to say, okay, what is MPH of 1.55 times, well, the square root of 25. So what is 1.55 times 5, square root of 25? Well, that's going to equal 707.75. So the speed of a 25-foot canoe in still water is 7.75 miles per hour. So there's our function, our formula, and then we use it and we solve and we get the same thing that we got here. And then we rewrite our new formula and which is kind of covered there, but we use it to then solve and we get the same thing. The process on these can be more in depth, but my hope is that these variation problems are not ones that you struggle with. Let's do a try, except we'll call it an example. So in an electrical circuit, the current passing through a conductor varies inversely with the resistance. Suppose that when the current is 5 amps, the resistance is 32 ohms. What is the resistance when the current is 8 amps? So I have in an electrical circuit, the current passing through a conductor varies inversely. Okay, so current. So I have something that looks like, what would I call that? Let's just call it current right now while we're working with it. Current, and it's going to equal, and varies inversely. So this is where K times something with the resistance. Inversely with the resistance, so this is not times, it's inversely. It is K divided by the resistance. So this would be K over the resistance. Okay, but I know that the amperes are current, so that's a capital A, and the resistance is ohms, so this could be written as A equals K over ohms. Okay, so that's a nice formula. Now, I do know that when it's 5 amperes, the resistance is 32, so 32 ohms. So this gives me, using that formula, this gives me that 5 is equal to some K over 32. Well, then, to solve for K, I'm going to just multiply by 32 on both sides. That goes away, and 5 times 32 is 0, 1, 15, that's 160 is my K. This gives me the new equation, the more useful equation of A is equal to 160 over ohms. Now I can use that one to solve, because it wants to know what the resistance is when the current's 8. So, So I have 8 is equal to 160 ohms. And they're asking me to find ohms. So I would still multiply both sides by ohms. I would say, okay, let's multiply both sides by ohms. So this gives me ohms and ohms. Remember, that's just a variable at this point. That filters away. So I have that 8 ohms. And remember, ohms is a unit at this point. Oops. Ohms is a unit. Is equal to 160. So then I just divide by 8. That goes away. I end up that the ohms, or the resistance, is equal to, 8 goes into 16 twice. So 20. So then this is going to equal 20 ohms. And if we look here, kind of the same pattern I modeled, but this is all on here, so you can look at it. There you go. And we see that we got both this piece to figure it out. This is the formula right here. And then we have the simpler formula, the more useful one that we got here, using the information given. And then to find the actual resistance, we have this. All right. I hope this helps. Have a good day.